Okay, the next section is on coding, and we talk about we can have source coding, channel coding, and line coding. And the source coding is all about compression, all about sampling, digital sampling, and then compression. And channel coding is all about error detection and correction. And line coding is all about the encode the bit stream into digital waveform. Okay, and we'll see many line coding schemes here, and they try to some of them try to solve the problem we mentioned in the general issue about synchronization, baseline wandering, and DC components. Okay, so we will not talk much on source and channel coding, but we'll talk more on line coding. So source coding, as I said, for compression, that you need to sample the source data and then digitize. When you sample, you digitize, and then you want to compress so that you reduce the bit rate generated by that source. That's called source coding. And channel coding try to protect the digital data through a noisy transmission medium or stored in an imperfect storage medium. So in that kind of imperfect or noisy environment, you want to do error control, error detection or correction. So that's channel coding. And that error detection or correction is done at the physical layer, not at the link layer. So here we're talking about the physical layer scheme for error detection and correction. And no matter what kind of error detection and correction what kind of scheme you impose, because the overall performance is still limited by the Shannon's theorem. And remember, Shannon's theorem is about the imperfect channel, the noisy channel. In the noisy channel, there's a limit, an upper bound from the bit rate from Shannon's theorem. Okay, line coding. That's the main topic in this section. So by definition, line coding is to apply a pulse modulation to a binary symbol and generate a pulse code modulation waveform. Okay, now here you see a modulation, pulse modulation. So you might think, okay, modulation means that I transform digital waveform to analog waveform. So it's a little bit confusion here if you see a pulse modulation or pulse code modulation. But it's not to transform into the analog waveform. It's in a digital waveform. So in order to differentiate this kind of modulation with the other modulation we will see in the next section, usually we call this line coding is also called as baseband modulation. Baseband modulation, meaning that you generate the digital waveform. However, in the next section, it's called broadband modulation. Broadband modulation. So here, pulse code modulation, also called baseband modulation. And that pulse code modulation waveform are also known as line codes. Line codes. And doing this operation is called line coding. And there's a term or a performance index, a matrix defined here. It's called signal to data ratio. Signal to data ratio. Remember last week we talked about signal to noise ratio. in Shannon's theorem, we talk about the signal to noise ratio. If the ratio is high, then it means the channel quality is good, because the noise is much lower than the channel quality is good. And here the signal to data ratio means to carry that amount of data, how much signal you need to use. So the signal is the price to pay for the data you want to transfer. Okay, so here it's a ratio of the number of signal elements to the number of data elements. So you want to transmit data elements, but you need to generate signal. And the more signal element you generate for a fixed number of data elements, it would means that you pay higher, you pay more in order to do that. So if the signal to data ratio is high, then it means that it's expensive. So we are talking about an encoding scheme, line coding scheme. Then the line coding scheme is more expensive. I mean, pay more price. So you want to keep the signal to data ratio low, right? Your objective is to keep the signal to data ratio low. You want to use fewer signal elements to generate, to transfer more data elements. Okay, compared to signal to noise ratio, that you want to, the signal to noise ratio, well, the signal to noise ratio sometimes is mostly given. Well, the channel environment is this bad, then you can't do much about it. The signal to noise ratio will be low, but you can't do much about it. It's a given parameter. But here it's not a given parameter. It's things that you want to improve. You want to have a low signal to data ratio. Okay, so here's an example that you have the data. The data is 1010, and digital data coming into the line coding encoder, and then transmitted, and then if no broadband modulation. This is also sometimes called baseband modulation, as I mentioned, with pulse code modulation, PCM waveform. And then there's a decoder to regenerate the bit stream. And here you see if it's in order to transmit, if you say you take two signal elements to transmit one data bit, two signal elements to transfer one data element, then the SDR, signal to data ratio, will be 2. And if this I have one signal element to transfer one data element, then SDR is 1. And if this say I use one signal element to transfer 2 bits. Say this is 2 bits. I use this to signal 2 bits, and this is another 2 bits. Then SDR is a half, 1/2. Okay, so you will see that we would like this better than this and this. Now you want to use fewer signal elements to transfer more data bits. You will see there are some schemes, some line coding scheme that has this property. Okay, as we said, that line coding, the dominating game about line coding is about synchronization that you the received signal need to help. The received signal needs to help a receiver synchronize its clock with the corresponding transmitter clock. So with this in mind, then we see a whole bunch of line coding schemes, and from the unipolar to bipolar to polar, and some other more complicated schemes. Okay, so let's take a look at the examples, and you will see what they are. So the first one is the first line is the clock signal, and then the second line is the data stream in bit stream, and then you start from unipolar NRZ L. Okay, you see that we use a high voltage to signal 1 and 0 voltage to signal 0, bit 0. So that's the basic, the most straightforward one. However, this unipolar NRZ has the problem of what? It could lose synchronization. It has no self-synchronization, and it would lose synchronization if there are more consecutive ones or more consecutive zeros. Then the receiver clock will lose synchronization. The next scheme is a polar NRZ, meaning between unipolar means that you always go positive or 0. You don't go negative. But polar means that you go positive and also go negative. So you use a plus voltage, positive voltage to signal 1, and negative voltage to signal 0. So it's also straightforward. And another variation from polar NRZ is polar NRZ inverted. Okay, how is it inverted? It says that the signal will change only when it needs to transmit 1. The signal will change only it needs to transmit bit 1. So I have a signal change here, and then for 1, but no change on bit 0, and change on bit 1, I go negative, and no change on bit 0, and no change on bit 0, and change on bit 1, change on bit 1, change on bit 1, and no change on bit 0, change on bit 1. So this is polar NRZ inverted. However, this scheme also does not have self-synchronization either. If I have a consecutive 0, I lose synchronization. You have too many consecutive zeros. So the next one would have self-synchronization feature here. It's called polar RZ. It would return to 0. NRZ means non-return to 0. But RZ means it returns to 0 in the middle of the bit. So for bit 1, I use this pattern, positive first and then 0. For bit 0, negative first and then 0. Again, positive first, 0. Negative first, 0. Negative first and then 0. So that's polar RZ. It has self-synchronization. It will change, the signal will change in the middle of every bit, and also in the beginning of every bit. With this self-synchronization, of course, the price to pay is the SDR, signal to data ratio, will be 2. will be 2. SDR will be 2. Another scheme is called Manchester. It says that in the middle of the bit, I still transist. I would change my signal, but in the boundary of the bit, I might not change. Say Manchester and differential Manchester. Okay, Manchester says that it will go from, if it's bit 1, I go from low to high. Okay, low to high, low to high, low and then transist in the middle and then high. But if it's bit 0, I go from high to low, high to low. And differential Manchester says that, so the advantage of Manchester is that it has less transition. In order to, still it has clock synchronization, self-synchronization, but you don't need to transist twice for every bit. Okay, you might transmit once per bit, or between 1 or 2. Okay, sometimes you don't transist at the boundary. Okay. And differential Manchester says that, okay, in the middle, in the boundary of the bit, you only transist when the next bit is 0. So you only transist at the boundary. You only transist for bit 0. So if it's bit 1, I don't transist. Okay, here I transist, and here because it's bit 0, I transist. And then and I need to transist in the middle of a bit, and here is the boundary, and because the next bit is 1, I don't transist. I need to transist in the middle, and then here, because the next bit is 0, I need to transist. The next is 0, I transist. The next bit is 1, I don't transist. So no transition here. No transition here, no transition here. Okay, from Manchester or differential Manchester, you will see that the number of transition to send the same amount of data bit, the number of transition for Manchester or differential Manchester will be less than what? Polar RZ. For polar RZ, it will be 2. And definitely 2. No, it won't be less than 2. Every bit needs to have 2 transition. Okay, but Manchester and differential Manchester probably will be 1.5. Something on the average will be 1.5. And the next one is called AMI. See, it says that if it's bit 0, then 0 voltage. If it's bit 1, then I go to positive 1 or negative 1. Positive 1 or negative 1. Depending on where I am now. So for example, this will start from here, plus 1, positive 1, and then go to 0. And the next is also bit 1, and because I have been in positive 1 in the previous 2 bits, so now I need to go down to negative 1, and then go back to 0 for bit 0, and then because the next bit is 1, because I was in negative 1, so now I go to positive 1. Okay, so it's kind of, with this scheme, you need to memorize what is the previous one. For the previous bit 1, perhaps 2 or 3 slot or 2 or 3 interval before that, where I am, I was negative, now I need to go positive. And then you go negative, positive, 0. And now you go, because I was positive, now I need to go negative. So you need to remember something. It's kind of stateful. Okay. And with this scheme, it's still this scheme is not as good because you immediately see that it has no self-synchronization, right? If you have many consecutive zero, you will lose synchronization. Okay, another scheme is MLT3. It says that if it's 0, no change. Keep your signal label. If it's 1, you +1 or -1, depending on which direction you are going. Okay, so take this. If it's 1 now and the next bit is 0, then you keep the signal. Instead, unlike this, you go back to 0. Here you stay. So no change on 1. No change on 1. And then the next bit is 1. Then I would +1 or -1. -1. -1 or +1. Can I go +1? No, because probably this is the maximum voltage I can generate. So I need to go down. I can't go up, so I need to go down. So I go to 0 voltage. And the next 2 bits is 0, so I no change. And then now I'm going down. So the next bit is 1, I go down further. And the next bit is 1 again. Can I go down further? No, I can't. So I need to go back to 1, go back to 0. And the next bit is also 1. I can go up again to 1, +1. And the next bit is 0. I keep, no change. And no change again. And then the next bit is 1. Now I'm going up, but can I? No, I can't. So I go down to bit 0. And then, yeah, so this is MLT3. And this is not good either because of what? It no change on 0. I could have consecutive high voltage or consecutive 0 voltage if I have too many zeros. Okay, questions? Questions so far for line coding? So these are the basic line coding schemes. And there are a few more, which is sometimes called RLL, runtime length, and also block coding. They also serve a similar purpose. We will cover them next. But before that, there are a few slides talking about the bandwidth of line coding, or the SDR. So say these 2 figures. The upper one is for NRZ line coding, and the lower one is for RZ line coding. And the NRZ line coding says that that's this one. You need to check this. And polar RZ. So RZ, the polar RZ says that the SDR is 2. The SDR is 2, and here SDR is only 1. And you want to check the average baud rate. Here the average baud rate is the bit rate multiplied by the SDR and multiplied by the average factor. And the average factor is a half, 1/2. So you would have an average baud rate of bit rate multiplied by 1, which is SDR, and then multiplied by a half, the average factor, which is a half. So you got N/2, which is the average. So within this frequency spectrum, it says that if you do the integration on these to calculate the area under the curve, then you will get the average at n over 2. And here, if you average, then you got n, which is the average baud rate. Or the average frequency. Meaning that most of the bandwidth energy, most of the energy is centered around that frequency. And for Manchester and differential Manchester, it's SDR is also 2. And so its average baud rate is n multiplied by 2 multiplied by 1 over 2. So you got n. And there's an example, another scheme called 2B1Q. 2B1Q. It's a multi-level coding scheme that we haven't discussed yet. It's the first two, the 2B1Q, the first number 2 is the length of bit. How many bits? I want to generate 2 bits. 2 bits. Okay, which is binary bit. So it's the B stands for the binary bit. I got 2 binary bits and 1Q. The first one means that the signal length. I have a signal length. I only use one signal element, which is 1 here. And Q stands for quadrature. Quadrature means it's 4 level. The signal level is 4. The number of signal level is 4. So I would transmit 2 bit. 2 bit. Okay, the data bit is 2 binary bit with only one signal, and the signal level, the number of signal level will be 4. So I can use say I have 4 level, which is say +1, +3, -1, -3. So I can use one signal which has 4 different values to transmit 2 bits. So my SDR will be what? Signal is only 1, but D is 2. So I got 1 over 2. The SDR is only a half. Okay, and this is the scheme that you would use to transmit the signal according to the bit pattern. The bit you want, the 2 bits, the 2 binary bits you want to transmit. Okay, depending on the previous signal level, you can decide what to transmit next, what signal level you want to adjust. Okay, so the SDR is a half, 1 over 2. And there are also some other scheme that you could have, say, I want to have 4, say, this is an example of 4B3T. 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 It means that I want to transmit 4 bits by 3 signal, and each signal has the level of signal is 3, ternary. T stands for ternary. Ternary. So then I would send 4 bits. So the possible combination will be 2 to the 4, and then the signal level is 3, and I send 3 signal. So this is what? 16, right? The possible combinations. Well, 4 bits, consecutive 4 bits. Then the possible combination is 16, and here it's what? 27, right? Each signal has 3 possible values, three possible levels each signal, and I have three signal, so that'll be 3 to the order of 3, so that'll be 27. So I have 27 combination of signals represented by this, and in order to transmit just 16 pattern, this is larger than this, so it's okay, meaning I have more signal combination than number of data combinations, right? So I can pick, perhaps I can pick just 16 combination among these 27 combination to send the data bit. Okay. And there are also another combination, say AB6T, 8B6T. This is also 8-bit. So I have 8 to the order 8. That is 256. And this is ternary, 3 levels. And how many signal elements? 6. So that'll be what? That's 27 multiplied by 107. I don't want to calculate, but it's definitely larger than this. Okay. So this encoding scheme, say 2B1Q, you immediately see that the SDR is 1/2, and you can also calculate SDR for the other two schemes. Another scheme is called runtime length. Runtime length. It wants to limit the length of repeated bit to avoid a long consecutive bit stream without transition. So what it does is it transform or map a data bit stream to more data bit stream. Say I map every 2 bits into 4 bit, every 2 bit to 4 bit, okay, and every 3 bit will be mapped to 6 bit. So it's doubled. It's doubled. So the SDR will be 2, right? Because you pay double price to generate. So if it's 4-bit stream, then I map to the 8-bit stream. And the way I pick, because the space here, see, this is 2. If this is 2 bits, then the possibilities are only 4. But here if it's 4 bits, then the possibility is 16. So 4 mapped to 16, meaning among the 16 bit, I pick 4 of them. Among the 16 combinations, I pick 4 of them that have more transition. I mean, more, or enough transition. I don't want to pick too many transition, because I want to pick enough transition, just enough transition. Too many transition will again waste energy or waste bandwidth. So I want to pick just enough transition. Okay. Again, for these two, I pick the pattern with enough transition. This is the same. Every 2 bits are transformed into 3 bits. So 0, 0 is transformed into this. Well, depending on. So I transform this 4-bit transition into 6-bit, and 2-bit transition to 3-bit. So then the SDR will be what? Signal is 3 and data is 2, so it'll be 3/2. The SDR value will be 3/2. So the price you pay with this scheme will be less than this scheme. With this scheme, SDR is 2, but here the SDR is 3/2. Okay, which will be less than 2. So the price you pay is less. So you can immediately see that there are possible schemes that you can have SDR which is larger than 1 but not too large. I don't want to go to SDR value of 2, which is probably too expensive. I want to go down a little bit, say 1.5 or 3/2. So I want to keep the SDR value down. However, I still have the self-synchronization property, meaning that I have transition. I have enough transition to keep the clock synchronized. And another scheme is called block coding, which does basically the same. Which is the one example is 4B, 5B encoding, and it has a table saying to map 4-bit pattern into 5-bit pattern, 4-bit into 5-bit pattern, and then because here the combination are 32, the number of combinations are 32. I only pick 16 of them to represent data. Okay, so that's a hex data of 0 to hex data of F. So 16 combination, and while keeping the other half, the other 13 for other purpose or unused. Okay, so here you will see that I pick these 16. They have enough transition compared to the other bit pattern which are not picked. So I just pick those with enough transition. So 4B, 5B, you can see it's a kind of the block coding. This is called an example of block coding, which is similar to the scheme we in the previous page, RLL, runtime length. They all try to limit the runtime length, meaning consecutive 0 or consecutive 1s. Okay, and there are some other block coding scheme like AB10B, AB10B, meaning you map 8-bit pattern into 10-bit pattern, and for 10-bit pattern you only use the combination with enough transition in the middle. Okay, and the open source implementation, the first open source implementation in this chapter has a hardware design for AB10B line coding. Okay, so it's actually used in I think in Ethernet. Okay, and with that kind of sophisticated, then you will calculate, okay, what is the SDR for this? What is SDR? You will say that the signal is, the price you pay is 5 in order to send 4-bit data. So the SDR will be 5/4. 5/4. So it's slightly larger than 1, 5/4, but good enough for self-synchronization. So you don't need to go to 2, SDR value of 2 or 1.5. Probably just 1.1 or 1.2 will be enough for self-synchronization. And if you have those kind of sophisticated encoder, then you would just need to use a very simple line coding scheme, well, combined together. Say, I use a 4B, 5B block coding, and then use NRZ inverted to generate a digital waveform. Here, from here to here, I'm still generating bit pattern, right? Not waveform. The output of the 4B, 5B is only bit pattern, not waveform. Now I need to generate a digital waveform, and by a straightforward NRZ inverted, then I generate a digital waveform. So I can combine these two together to generate a digital signal. And it would have self-synchronization. The open source implementation here is a AB10B encoder. It's used in gigabit Ethernet and PCI bus, express bus, and some other standard like IEEE 1394B and serial ATA. So it's actually used in many standards, the AB10B, and it provides clock synchronization and also DC balance, meaning on the average the number of ones and number of zero are about the same. If on the average the number of ones is higher than the average number of zero, then you would have a DC bias, which is positive. Plus. Then it's not DC balanced. And this scheme say that it's because the bit pattern you pick in general, on the average, you have the same number of ones and the same number of zero, then you can reach DC balance. And here's the block diagram of this AB10B encoder. And this open source implementation is grabbed from the opencourse.org, which is a website that has the open source hardware implementation. The design here is to split, divide and conquer. Instead of, I want to have 8 input, 8-bit pattern, and then generate, and then pump out 10-bit pattern. So the input is 8 bits and the output is 10 bits. And I need to do the mapping. And in the mapping, in the book, you will see that the mapping is actually done by you hardwire, hardcode in a program, very low program, by doing AND or NOT logical operation to map the input bit pattern into the output bit pattern. So they are doing that kind of logical operations. However, if it's 8 bits and inputs and 10-bit outputs, then the operation, the mapping will be quite complicated and with a more logical operation, with more logical operations. So the way to reduce the complexity of the mapping is to decompose into 2 blocks. Okay, 8B, 6B, and 3B, 4B. So I split the 8-bit into 5-bit and 3-bit input. And then for the 5-bit input, I generate the 6-bit output. For the 3-bit input, I generate the 4-bit output. And then combine them together, I form the 10-bit output. And because the size is reduced here and also here, so the number of logical operation in order to do the mapping will be reduced. The number of logical operation will be reduced for the mapping. And of course, the cost is reduced. Okay, so that's the way they implement this You can also check the book to describe how those logical operation works.